the function that you're interested in. So, so one of the main points is that convergence, okay, of asymptotic series is not necessarily important, okay? And the example we took for this, right, is the Euler series, the one in particular that we were showing, which stated that s of x equal to integral from 0 to infinity e to the minus t over 1 plus xt dt, okay, can be written as asymptotically n equals 0 to infinity minus 1 to the n factorial x to the n, right? So this does not converge, okay? But the remainder term, which we said Rm of x, this is bounded from above by m plus 1 factorial x to the m plus 1, okay, will be small for small x and finite, okay? And one idea is that sort of the optimal number of terms can be found by trading off the blow up of m plus 1 factorial, okay, and the decrease of x to the m plus 1, right? So for any particular x, there's going to be a choice of m that minimizes that remainder. And so oftentimes for asymptotic series, you want to take a different number of terms depending on the particular value that you're plugging into the approximated function. Okay. So in general, we're going to see that for asymptotic series, sometimes you can derive multiple asymptotic series for any particular function. One of those may be divergent. One of those may be convergent. But the divergent series may be a lot better approximation if you only save 2 or 3 terms in the asymptotic series. So again, that emphasizes why it's important that we're not necessarily worried about creating a convergent series, just one that is accurate when we retain a few terms, okay? So we'll unpack that a little bit more in an example that we come across as we look at asymptotic approximations of integrals, okay? And okay, so let me just recall, right, in general, that convergence, right, implies that some series fn of z, some from n equals 0 up to infinity, okay, it converges at z if given epsilon greater than 0, we can find a number and 0 z of epsilon such that the following thing is true. The sum from n equals m up to n f n of z is less than epsilon for any m and n greater than n0, right? So the point is that the limiting terms as we go out to infinity, they're always going to get progressively smaller, okay? And in general, a series is going to be said to converge to a function, f of z at z, okay? A series converges to a function, f of z at some value of z, if given epsilon greater than 0, we can find a number and 0 z epsilon such that the following thing is true, so slightly different statement. N equals 0 up to n fn of z minus f of z is less than epsilon for any n greater than n0, okay? Therefore, okay, series converges if terms decay rapidly as n goes to infinity, okay? And that's the problem, or that's the breaking of convergence that we had with the previous example. The coefficients are blowing up. They're scaling at a rate that's faster than essentially than the ones that we just the term x to the m, right? So this brings us to motivation for different approaches, okay, to approximate integrals, okay? And to take an example, let's consider the error function, okay? So proving convergence in general is not that useful, okay, for asymptotics, right? We've already sort of made that point, right? Let's look at it in the case of an integral, okay? So the error function integral, define that as 2 over root pi, integral from 0 to z e to the minus t squared, okay? And we can note that e to the minus t squared equals the sum from n equals 0 up to infinity minus t squared to the n divided by n factorial, okay, by analyticity, okay? And in fact, this has an infinite radius of convergence, okay? So therefore, we can actually write that the error function of z is equal to this infinite series, okay? Z minus c cubed over 3 plus z to the 5th over 10 minus z to the 7th over 42 plus so on and so on, okay? And we get this by performing term by term integration, okay? So this might be the very first thing you try for an asymptotic series for an integral, right? You know, we can take this integral. There's sort of other ways to do it with special functions, right? Well, let's say we had some integrand in here that we didn't think that we could integrate, okay? But that we had some straightforward way of obtaining a Taylor series, okay? We obtain that series, okay? And it's just, you know, a power series, algebraic, so we can then plug that in and then integrate it term by term, okay? And this is the result that we get. And we look and we see that, well, I know I had an analytic function. And so therefore, I can just take its radius of convergence, and that should be where this is well defined, okay? So why wouldn't I just stop there and say that's a great series, okay, to use in order to approximate? Well, if we look at using 8 terms of this series to approximate, the accuracy that I get is approximately equal to 10 to the negative 5th if I choose z equals 1. So that's how large of an error that I'm going to make, okay? But for 10 to the minus 5th accuracy at z equals 2, okay, I need 16 terms, okay? And then at z equals 3, I need 31 terms, okay? And at z equals 5, I need 75 terms, right? So you may say, well, okay, that's to be expected because you're making z large, and so your Taylor series is sort of breaking down for those large values. But I know that I have convergence there, so why isn't, you know, sort of convergence good enough to give me an accurate approximation at you know, fairly large values of z? Okay, so convergence isn't necessarily a guide to accuracy of asymptotic approximations. The other thing is that round-off errors will also disrupt approximations, right, on computers, right? You have machine precision, okay, and you have to face the reality that you're going to have to pass these asymptotic approximations probably through whatever Python or, you know, MATLAB or Mathematica or Maple or whatever, okay? And you're going to be working with computer machine precision, okay? So that creates a problem, right? If I need to go out to 75 terms, surely z to the, you know, 101st power is not going to be very accurately computed, okay? And so I can go out to many, many terms, but they may not get computed very accurately, and then it's pointless to try and go out to many terms. So that's why, in general, asymptotic approximations, you're really only, you know, kind of supposed to go out to 2, 3, 4 terms or something like that. You kind of know that you're going to run into this wall of machine precision if you try and maintain too many terms, okay? So the question is, then, can you come up with better approximations? And of course, that's like the whole point of this section, is that you can, right? Like the main thing that you would think of if you just, you know, sort of came from a calculus class is not always the thing that you should do in this case. So let's rewrite this integral slightly differently and just say, well, I can compute the integral from 0 to infinity. It's just 1. I'm going to subtract off, okay, the integral from z to infinity. And then another thing we can try is integration by parts, okay? a natural way of creating a series from an integral is to integrate by parts, and each of the boundary terms that you create from that integration by parts comes another term in the series. And if the integral that's left over at the end of that is smaller than the original integral, you're sort of successively creating an asymptotic series with each action of integration by parts. So the integral from z to infinity of e to the minus t squared is equal to, okay, the integral from z to infinity of, now I'm going to write it like this, 2t e to the minus t squared divided by 2t, okay? So now I have my two terms that I can separate, and I get e to the minus z squared over 2z, okay? I think I need a minus, yeah, I need a minus sign. I can't do it. Okay, and then I'm gonna get I get a plus here, integral from z up to infinity, e to the minus t squared 2t squared dt. All right, so yeah, I had a minus term to start with, integrated up, I got rid of one minus term, but then I differentiate and I created another minus term. Okay. All right, so you see what happens here, right? Is we have created this term. The question is this new integral smaller than the original one? If it is, you can think of this now as your remainder term, okay? So if we just continue on, the idea then is that you're always going to have this term e to the minus z squared out in front, okay? You're going to have a z out in front, and then you have a square root of pi. And then the expansion is going to go inside of the parentheses like 1 minus 2z squared plus 3 factorial 2z squared squared minus 5 factorial 2z squared cubed plus and so on, right? And in fortunate cases, right, you can pick up on this pattern and figure out how this generalizes, this integration by parts generation of boundary terms sort of generalizes across any number of integration by parts. But in practice, if you only care about getting the first three leading order terms, you just go the brute force track of just performing that integration by parts, okay? And obviously, you always have many choices for integration by parts. So sometimes this is a trial and error. You may choose the sort of wrong way to do integration by parts. You may think that you need to integrate the exponential term, but you actually needed to differentiate it or something like that. But this asymptotic series now works well, okay? But let me point something out. This series, okay, it diverges for all z, okay? So if I carry this out to all of the terms, right, my radius of convergence is 0, okay? And it actually, you can see that you would expect it to get worse, especially as z goes to 0, okay? But the thing is that the leading order term is sort of nearly correct, and the next few terms, okay, get closer until the series diverges, right? So this is true for large z, right? If z is large, then, you know, if I take z to be 5 or whatever, then this integral is going to be relatively small. So already I should expect the integral to be, you know, roughly 1 in this case. And I just need some exponentially small corrections here that I can pick up by adding on these extra terms. Okay, so Sure, it works for larger values of z better, but it will still work for small values of z. So for 10 to the minus fifth accuracy, we just need 3 terms for z equals 2.5, and in fact only 2 terms for, let's say, z equals 3. Okay, so you can plug everything in and work it out, but the point is in general that you need way fewer terms in this case, and this looks a lot different, right? This is no longer a power series, just, right? It involves now this exponentially small term, so it becomes clear that you could never quite have captured this very accurately by just performing a power series, right? You need this additional transcendental function. And that's something that integration by parts creates for you that you're not going to get from a standard Taylor series expansion. Okay. Let me take a breath. Are there questions at this point? All right. Okay. So, I mean, the approach is, it's relatively systematic, but it's powerful. Okay. So let me remark on sort of another general case, okay, that's sort of related. If f of epsilon is differentiable, okay, near epsilon equals 0, then the local behavior near epsilon equals 0 can also be studied using an integration by parts approach. Well, what do you mean? F of epsilon is just a function, right? So how am I going to sort of fit integration by parts in? Well, we just rewrite the function as an integral, right? A definite integral, okay, over this dummy variable of f prime of x from 0 to epsilon, and then we remove the f of 0 part. So if we integrate by parts, f of epsilon, right, is equal to f of 0 plus epsilon, x minus epsilon, f prime of x, integral from 0 to epsilon, plus integral from 0 to epsilon, epsilon minus x, f prime prime of x dx. Okay, so what's going on? It looks like we're sort of generating something that kind of looks like a Taylor series, but we're building in these terms that depend on this integrand, which may be sort of non-standard, right? And they speak to the particular character of the function itself. So you're sort of building up an asymptotic approximation of a function with the sort of features of the function in mind. So if we repeat this process n minus 1 times, then we get f of epsilon equals the sum, that sigma, okay, we get the sum from n equals 0 up to n, epsilon to the n, f differentiated n times at 0 divided by n factorial plus now this remainder term, which is 1 over n factorial, integral from 0 to epsilon, epsilon minus x to the n, f to the n plus 1 derivative of f, okay? So the key is, sort of looking at this remainder.
Isn't this just Taylor's theorem?
Yeah, right. Yeah. So this is the idea, right? Is that you're you're sort of getting this from a Taylor series, right? But when we apply this to the parametrized function that we have in more general integrands, then you're going to get this additional term that comes in based on the whatever the form of the integrand is. But yeah, right. This is showing that we can sort of draw a parallel between what's happening in integration by parts and yeah, exactly what you would get from Taylor series. But the result is different than just sort of Taylor expanding an integral and integrand and then integrating it is my point. Okay, so if the remainder exists, right, for all n, f of epsilon can be written now, right, as this Taylor series, okay, as epsilon goes to 0, okay, and small epsilon greater than 0, okay, if we have a convergent Taylor expansion about epsilon equals 0, okay. So so this integration by parts, right? It generates for us a Taylor series expansion in this case, right? But in other cases, right, where we sort of split the integral in different ways, we can get any number of sort of series expansions. So this is sort of a generalization of the mechanism that you could use to generate a Taylor series. But now we have a whole suite of possible expansions that we can get depending on how we split up our integrand. Okay, so just to drive this point, let's look at another example where we have just an exponential in our integrand. And in particular, we want to perform this expansion for large x, right? So if we tried to Taylor expand this around x equals 0, there's a problem, right? Because we're trying to perform a large x expansion. You might say, well, we could, sort of change variables, take x to be 1 over y or something like that, and you could try a Taylor expansion around there. But remember, you run into issues trying to perform expansions of exponentials out at, the argument being negative infinity. So let's try our integration by parts approach. And in particular, we're going to split the integrand up into 1 over t cubed and the derivative of e to the minus t to the 4th dt. We have this extra factor of minus 1/4 popping out. So the result is we have these boundary terms, e to the minus t to the 4th over 4t cubed, evaluated at the boundary terms, will vanish in infinity, and we'll get something non-trivial on the x boundary. And then in our integrand, we have e to the minus t to the 4th, t to the 4th, dt, okay? So if we clean this up, we end up with e to the minus x to the 4th over 4x cubed minus 3/4 integral from x up to infinity, e to the minus t to the 4th over t to the 4th dt, okay? So now this first term, right, this is what you would call our leading order asymptotic approximation. And we know that that's true because the integral from x up to infinity, the second term here, okay, is bounded from above by 1 over x to the fourth, x to infinity e to the minus t to the fourth dt. So this is equal to, okay, I of x is divided by x to the fourth, which is much less than I of x for x goes to infinity, okay? So the point is that your second term here needs to be much smaller than the first term for this to be a useful integration by parts. Otherwise, your integration by parts is not really generating an asymptotic series because successive terms are not, you know, smaller than the previous terms. And in particular, they have to have, you know, order smaller than the previous terms. Okay, or, you know, little o of those previous terms, if you wish. Okay, so this is different than what we would get from just expanding this out and performing term by term calculations, right? And also the you know, the approach of just using one as your function that you integrate up, and then this as your derivative term, right, is just a very specific case of integration by parts. So the general example that we showed before, right, is just showing that term by term is also a specific form of integration by parts, okay? But it's a very narrow and not necessarily always very useful way to approach this, okay? So you could integrate further, okay, to produce more terms, okay? And they would successively be smaller than the previous ones, okay? Telling you that you've sort of picked the right way to split this integral up, okay? Now, to compare to just term by term approach, okay, consider a number of integrals, okay? We may have the integral from a to infinity of f of t dt, or the integral from a to b of f of t dt, okay, where f of t goes to infinity as t goes to, I'm going to run out of space here. Where t, as t goes to c, f of t goes to infinity, for a is less than or equal to c is less than or equal to b. Okay. So there's some cases here, right, where these integrals exist and converge, okay? If the limit as x goes to infinity of this integral for the limit as x goes to c. Exist, okay? And this is called the principal value, okay? Now, for instance, if f scales like a over t to the alpha as t goes to infinity, okay? Then the integral from a up to infinity of f of t dt converges when alpha is greater than 1 and diverges when alpha is less than or equal to 1, okay? Also, if f of t is much less than 1 over 2 to the alpha, okay, it will be convergent if alpha is greater than 1, okay? Second, if f of t is approximately equal to a over t minus c to the alpha, or it scales as that as t goes to c, then the integral from a to b of f of t converges when alpha is greater than 1 and diverges when alpha, sorry, when alpha is less than 1 and diverges when alpha is greater than or equal to 1, okay? So this is like if you have some internal singularity of your integral, okay? This gives you a rule for when you have a convergent or divergent integral, okay? And also if f of t is much less than 1 over minus c alpha, then it's going to be convergent if alpha is less than 1, okay? So this is all sort of a something to caution you about, right, as you build up these terms, because as we do this, right, we can start to generate from our integration by parts these reciprocal terms in t to the fourth. Now, fortunately, in this case, we have a scaling by an exponential, and so everything is going to vanish fast, right? But as you're creating additional integrals through integration by parts, you do have to worry about the scaling. So before you sort of choose which way to integrate and how to split up your functions and which one to differentiate and which one to integrate, okay, you have to think about this, because otherwise you're going to be creating additional terms in your asymptotic series that are divergent. And it's not going to be any help if you tack on an additional term that's just the same size as your leading order term. Then you don't really have a separation of leading order terms and remainders, okay? So, that is, should be some consideration when you start to create these additional terms from integration by parts, okay? So just to drive home the main result that we have here, okay, if I define some integral, okay, from a to b, let's leave x out of the limits for now. And it's some function, f of x t. I'm just integrating in t from a to b, and I want to approximate this, okay? Well, if f of x t can be approximated by the sum from n equals 0 up to infinity of fn of t x minus x0 to the alpha times n, okay, as x goes to x0 for alpha greater than 0, okay? And this is uniformly valid for t living in a to b, okay? Then I of x is going to be equal to the integral from a to b, okay, of f of x t dt n equals 0 up to infinity x minus x0 alpha n integral from a to b fn of t dt as x goes to x0, okay? So this is not necessarily your standard Taylor series, okay? Could be really any scaling here, so you may have, you know, additional squared or sort of fractional terms each time, okay? But remember that what we derived before, it involved these reciprocal terms, okay? So before we sort of dive into the more general result for integration by parts, let's look at another example, which is going to be slightly different than the one before, but we still are going to have some exponential function, okay? So let's say that we have this, this definite integral, but we have some parameter m that we want to treat as our variable that we're going to approximate in. And m is going to live in the interval from 0 to 1, okay? So this is sometimes called the complete elliptic integral, okay, of the first kind, okay? And if we start by just performing a term by term integral, okay, that can work in this case, but it's not necessarily going to be a uniform approximation. So let me show you what I mean, okay? So if we examine some sort of term by term approximation, k of m is going to be approximated by just a Taylor expansion now of our integrand that we then integrate up term by term. And let's just take the first two terms of the Taylor series approximation, okay? Where the variable that I'm expanding in is m in this case. So this is then equal to pi over 2 plus m over 2 pi over 4 is equal to pi over 2 1 plus m over 8, okay? But what happens as m goes to 1 from below, okay? Well, 1 minus m sine squared of theta to the minus 1/2 is equal to 1 minus m minus 1 sine squared theta minus sine squared theta to the minus 1/2, okay? This is equal to cosine squared theta plus 1 minus m sine squared theta minus 1/2. And this is equal to cosine theta to the minus 1, 1 plus 1 minus m tanh squared theta to the minus 1/2. And we can approximate this as cosine theta to the minus 1, 1 minus 1 minus m over 2 tanh squared theta, okay, as m goes to 1 from below, okay? But this is not going to be uniform for theta is in 0 to pi over 2, okay? So this maybe gives a clue towards the problems that you can encounter with term by term expansions, which is that your Taylor approximations, right, that you use for your functions that live in your integram, okay, because you're expanding in a parameter, but then you also have the variable of the integrand, right, where your term by term expansion is valid, okay, may only be in portions of the domain that you're having to integrate over, okay? And so you can sort of rescue this in term by term expansion sometimes by splitting things up into different expansions depending on whether you're on the boundaries of the integral or whether you're on the interiors, these sort of boundary layer methods, right? But that can get messy. But in general, you run into less problems like this when you're doing integration by parts because you just have more flexibility. You have more choice in terms of how you expand your integral, and you can do it in a way that will respect these sort of scaling rules of the integrand at different parts of the integral. Okay. So I know this is a lot of preliminaries for now, but on Wednesday, we'll start getting more into the mechanics of integration by parts. The main point of today was to show the sort of differing things that you have to worry about whether you perform sort of term by term expansion or integration by parts in general. All right. Any questions before we wrap up for today?
Can you show me the previous slide again?
Yeah.
Cool, thank you.
Yep. All right. Okay. So homework. The next homework, it should be posted up on the Canvas page. I'll get the solutions up for homework 1. They may change if I catch any errors as I'm marking, and then I should have your homework marked by Friday. So you'll get some feedback on that. But we should be about kind of halfway through the material that you need for homework 2, if you want to go ahead and get started with the first few problems. Okay. All right. Well, I have office hours today at 4 as usual. So I may see you then, or otherwise I'll see you on Wednesday. Thanks.
Thanks, Zach.